I would like to start with an outline, so the talk will be split into 3 parts. So the first part will be some background. And then for the second part, I will give some motivation for the problem that I will be talking to you about today. So motivation. And the third part will be the problem. All right, so without further ado, let's start with part 1. So I hope some of you or most of you are familiar with the functional calculus for a single self-adjoint operator. So the Weyl functional calculus extends this idea of what it means to not just take a function of one self-adjoint operator, but possibly n of them that don't need to commute. So if we have a1 to an self-adjoint on a Hilbert space, and for any vector xi that I pick up, the linear combination xi a1 up to xi n an is essentially self-adjoint on a common dense domain D in H. Then, if I have a Schwarz function on Rn, I define what it means to take this function of a1, a2, up to an as follows. So it's the following integral. And this here is a Wigner integral. Wigner integral. So if you have a Schwarz function, you first take the Fourier transform of f. And then as you take the Fourier inverse, instead of taking the normal Fourier inverse, you put here an operator-valued kernel, which is e to the I xi dot a, where xi dot a is the closure. So this gives you a map from Schwarz functions to operators, and we say that f is the Weyl symbol of f of a with respect to a1 to an, or equivalently, that f of a is the Weyl quantization of f with respect to a1 to an. And an example of this, sort of the prototypical example, is, so example, if we take our Hilbert space to be L2, and you choose your first operator to be the position operator, and your second operator to be your momentum operator, then this map, which takes you from f xp to f of big X, big P, is none other than the standard Weyl quantization for pseudo-differential operators. So is the standard Weyl quantization for pseudo-differential operators. And this has been mentioned, I think, a few times so far in this workshop, and you might see either this notation, which is f of big X, big P, or you might see f of little x, ht, or you might even see up sub w of f. Okay, so this is all well. I can define this way of taking functions of a tuple of self-adjoint operators. But of course, one question I would like to ask is, can I do anything with this calculus? So one question that I can ask is, if I take two Schwarz functions, f and g, I quantize the first, I quantize the second, and I compose them. Does this operator have a Weyl symbol? In other words, does my functional calculus have a multiplicative structure? Can I define some notion of skew product or non-commutative product on my space of symbols, which in this case is Schwarz functions, such that if I take these two functions and multiply them with this product and I quantize it, I get nothing but the composition. Now, of course, this product cannot just be f times g, because these two operators don't need to commute. So I will now restrict myself to a setting where the answer to this question is always yes. So answer, yes, if the tuple ia1 to ian generate a unitary representation pi of h, pi on h of an n-dimensional, simply connected, nilpotent Lie group G. And let me just for now denote its Lie algebra as well. So the message is that this functional calculus will be multiplicative if I know that the self-adjoint operators that I'm working with generate the symmetries of a Lie group, and in particular an nilpotent Lie group. So I would like to state the precise statement for this, and this is a theorem. So Robert Anderson was one of Edward Nelson's students, and from my understanding, we also have another member in the audience who was also a student of Nelson. But the theorem says that if I have f and g, which are Schwarz, and star holds, and star is this, then there exists a unique h, which I denote as f star g, which is also Schwarz, such that g of a composed with f of a is nothing but h of a. And there is actually an explicit expression for h. Now, I apologize for splitting the theorem, but I was told not to write in the corner. So this is the continuation. So where we have an explicit formula for h, which is 1 over 2 pi to the n over 2, times the product of the Fourier transforms of h and g, except in the argument of the Fourier transform of f, we put this, which is a vector-valued polynomial in xi and eta. So I would just like to tell you a little bit what this polynomial is. So we have a Lie algebra and a fixed basis. So if I identify my Lie algebra with Rn with respect to some basis, so any vector in Rn, I map it to the linear combination. Then P of Xi eta, and these are two vectors in Rn, so this is in Rn, this is in Rn, is defined as follows. I take these two vectors, I identify them with their elements in the Lie algebra. So I take phi of Xi, and I take phi of minus eta. Then I exponentiate them, so I send them to the Lie group. I multiply, and then I go back. And just as a remark, here, because the Lie group is simply connected and nilpotent, the exponential map from the Lie algebra to the Lie group is a global diffeomorphism. So this is here well defined, and you can see why the nilpotency is important, because the moment I multiply these two elements and I have the Baker-Hausdorff series, from the nilpotency, the series is going to terminate after a finite number of terms, and that's why when I go back, I just get a vector-valued polynomial, and this is the one that goes in the definition of my skew product. And maybe as a remark, I can write it here, or actually I can just erase. Yes. I haven't practiced that enough. So just as a remark, P, and hence the skew product only depend on the group G, and the particular basis for the Lie algebra, and not the particular representation. So even if I work with even if the operators generated a different unitary representation, as long as they map from the same basis, this skew product on my space of symbols will be the same.
The representation must be somehow non-trivial. I mean, if I take the trivial representation, it gives me...
Right. I mean, it has to be a faithful unitary representation, yes. So I think with that, this concludes sort of this first part. So thank you for bearing with me. So now I would like to move to something a bit more exciting, perhaps, and this is the motivation of the problem that I would like to talk to you about today. So maybe part two.
Sorry,
yes.
Just make sure I understand. So if you look at the expansion to order 1 in h bar, do you get just the bracket between the x's? If you take as your function f and g, just say x1 and x2, is the symbol for the product to first order something like the bracket between x1 and x2?
Yes, and this is the special case when your self-adjoint operators are the position and momentum operators. So in this case, this skew product will be the Weyl product. But in this context, this functional calculus is for an arbitrary tuple of self-adjoint operators.
I guess that's what confuses me. But I mean, but because you have a Lie algebra homomorphism from G to your operators, right? Then you would just get the Lie algebra bracket in G.
Yes, yes. So here you in theory have the Baker-Hausdorff expansion in these two elements, and the group you're working with could be two-step nilpotent and step nilpotent, but as long as it's nilpotent, you will get some polynomial.
So to first order, it's the Poisson bracket on the dual.
Yes, yes. Okay.
You know that this fails for compact Lie groups?
Yes, which is why they cannot be simply connected and nilpotent.
I mean, you know that the formula fails?
Yeah. So in this case, I'm only looking at simply connected and nilpotent Lie groups, which guarantees that the exponential map is a global diffeomorphism from the Lie algebra to the Lie group. Yeah. So for example, SU2 is out of the question. So motivation. So this is positive representations of quantum states. Okay, so I would like to start the motivation by telling you a little bit about the Wigner distribution. So I will start by describing it in some words, and then I will write the formula for it and explain. So the Wigner distribution so is an attempt at writing a joint PDF for the instantaneous projective measurement of the operators A1 to AN. And here I will put time equals to 0, just to give the picture that we have an experiment in which we are trying to instantly and simultaneously fully projectively measure the N operators. And I will write down a formula for the Wigner distribution.
Excuse me. What is PDF?
So question, what is PDF?
What is PDF?
Probability density.
Oh, probability density function. Sorry. I meant, yeah, a joint PDF, probability density function. Sorry, it's probably not clear. So, okay. So suppose someone gives you n random variables. Now this is classical probability and asks you to write a joint probability density function between them. One thing you can do is write the characteristic function of these n random variables and then take the Fourier transform. And that will give you a positive distribution that integrates to 1. Now, the Wigner distribution is what you get when you try to apply the same steps, but you replace the n random variables with self-adjoint operators. So here you can see first, you try to take a characteristic function, chi of xi, by taking the expectation of e to the ixca, and then you take the Fourier transform. Now, unlike classical probability, even though most of the time you will get an object that integrates to 1, almost always it will be sign indefinite. So the first problem, or the first, not problem, observation, is that the Wigner distribution is sign indefinite. And the reason why it's sign indefinite goes back to Bochner's theorem, which says that what we think we wrote down here isn't a true characteristic function. For it to be an actual characteristic function, it needs to satisfy properties specified by Bochner's theorem, one of which is that this function must be a positive definite function. In other words, it must induce a positive kernel on Rn cross Rn. So the problem here is that chi fails to be positive definite, in the sense of Bochner's theorem. Now, despite this, I would like to tell you about other properties of the Wigner distribution, which make it very useful. And one of which will tie back to the background that we discussed. So this is maybe a key property. By construction, the Wigner distribution, when integrated against the Schwarz function, is nothing but the trace of rho against the Weyl quantization of f. So it gives us a way to do a correspondence from quantum-looking expectations in which you take the expectation of your operator against a density operator, into a more classical-looking expectation in which you integrate a random variable against a joint PDF. Now, of course, when I discuss the Wigner distribution in this generality, we have an arbitrary tuple of self-adjoint operators, but when you see it in textbooks, oftentimes n is 2, and the first operator is the position operator on L2, and the second operator is the momentum operator. And in this case, the Wigner distribution with this choice has a remarkable property, which is that even though it's sign indefinite for most states, if you convolve it with a bivariate Gaussian, and its variance is large enough, it will make the Wigner distribution positive for any rho. So this is the remarkable property in this setting. If I convolve, so now this is convolution, my Wigner distribution with a Gaussian, with a bivariate Gaussian that has some variance, so this is Gaussian, then this is positive for all rho if and only if the variance exceeds h bar over 2. So the moment you see this and you think, well, I started with an experiment that is somehow forbidden because I'm asking to measure projectively a set of non-commuting observables at the same time, suddenly I do this smearing and I wipe out all the negative mass from the Wigner and I get a positive representation of my quantum state rho. So this suggests that there should be some experiment that has to do with measuring these n observables that has, as a law on its outcomes, this law. So this is positive for all rho and integrates to 1. And I would like to tell you a bit about what this experiment is.
So the S is in the Schwarz space?
Which one, sorry?
S, space S.
Yes, this is the Schwarz space on Rn. Yeah, f is the Schwarz function.
So didn't that convolution not simply applying a certain semigroup to the state?
Well, yes. So this is exactly what I'm going to get to. So I'm going to explain why the sufficiency condition here is in fact trivial, because you can rewrite this as follows. So thank you for
Spoiling your fun, yes.
leading up to this. So it turns out that if you parameterize your variance as follows, h bar over 2 tanh of h bar t, and look at the Wigner distribution convolved with the bivariate Gaussian, parameterized by this t positive, then this can be written in the following form: trace of rho e minus t, and this is x minus x squared plus p minus p squared divided by the integral. Squared plus p minus p prime squared dx prime dp prime. So it turns out, and I would like to call this function h.
Sorry, something there should depend on G.
Yes, so G is a bivariate Gaussian.
No, sorry, not G, F, the function that you start with.
So,
Rho. Oh, I see.
right, so here, this was this general property, as you said, for any f, that I can have this correspondence. So right now, this particular f is a shifted Gaussian. Yes, so this is why I have a convolution here. So the way you see this equality is by observing that the shifted Gaussian in this integral is simply the Weyl symbol of this operator normalized by this number. So this, the moment you see this expression, you see that no matter what t is, the variance is always bigger than h bar over 2, and the right-hand side is manifestly positive for all rho and integrates to 1. So this is positive, integrates to 1. And it turns out that this expression is the joint PDF, or is related to the joint PDF of continuously measuring or monitoring x and p for t seconds. So now, a lot of people like to use this object as a positive representation for their states and set sigma squared to be this lower bound, h bar over 2. And in this case, the function h is called the Husimi function. So when you take the convolution with the Gaussian that has the smallest variance, this is the Husimi function. And the moment you see this, you realize, OK, it appears that this is the limit as this one goes to infinity, as t goes to infinity. So this is the limit as t goes to infinity of h t rho. And from this, the moment we saw this, we realized, OK, we might have a good idea of what the Husimi function is, not just for x and p, but for a general tuple of self-adjoint operators. And this is what I want to tell you about next. So I'm going to tell you about the Husimi function, and I'm going to write in words what it is. So So the Husimi function is not an attempt anymore. It is the joint PDF of continuously and infinitesimally measuring the observables A1 to AN forever.
What does that mean operationally? I mean, how are you observing, measuring these things?
Right, so mathematically, a weak measurement or an infinitesimal measurement channels your density operator rho through a selective Krauss map, which doesn't collapse rho to a particular eigenprojector of your operator, but it collapses it to a linear combination of all the eigenprojectors. So it's a weakened version of the projective measurement channel that you apply to rho when you make a strong measurement.
Some kind of particular POVM?
Yeah, absolutely. So a weak measurement is described by channeling rho through a selective Krauss map in which you put here a linear combination of all the eigenprojectors of your observable centered around some number. And the same here and the same there. And when you take the limit of how this rho changes, when this variance here is very large, so you have some t here, as the limit as t goes to dt, you can derive a model that which continuously and infinitesimally extracts information about the observable that you're monitoring. And when you compose two of them, one for x, say, and one for p, in the limit, you get a master equation that allows you to do both at the same time. So I would love to have more time to get into the detail. And in fact, it's great that you asked this question, because now it's a good time to advertise a paper that we uploaded yesterday night. So this is on the time-resolved interpretation of the Husimi function. And we uploaded it yesterday night, and this is joint work with Olga and Trifon. So it might take a few days to appear in case you're interested, but if you would like to take a look at some of the computations, I'm happy to give you a copy even today after this. So in this paper, we propose a natural class of positive representations So we propose a natural class of positive representations and prove that when you take the limit as t goes to infinity of the following expression, h t rho of A equals trace of e to the minus t ai minus ai squared divided by the integral dA prime. We define this general expression for any collection of self-adjoint operators and show that as you take the limit as t goes to infinity, for x and p, as we just saw a few boards ago, this converges to the Husimi function. So h t rho converges to. In the case of x and p, the well-known Husimi function, if the three operators are the spin operators, you converge to the Husimi function of a spin half particle, which is well known in the literature. And if you take here just one self-adjoint operator, this function converges to the Born rule of quantum measurement. Quantum measurement. Oh, my chalk is running out. So the moment we saw this, we realized that this definition of the Husimi function extends the Born rule for projective measurement into the non-commutative setting. And the central object of this expression is this operator, which I call the Gaussian semigroup.
I mean, the spin 1/2 case. I've understood earlier that we had to work in a nilpotent setting, and SU2 was not included. Right?
Absolutely.
Like
So the nilpotency requirement is there so that my functional calculus has a skew product.
Okay, but I'm so confused. I mean, you said SU2 is not in the cards.
Right.
There
So
it is on the board. So.
yes. So the nilpotency requirement is there only if I require a skew product on my space of symbols. Otherwise, the only thing I need to define this object is for this expression to be essentially self-adjoint, so that I can defines for me a C0 semigroup. So at the level of this expression, which is what we have in the paper, we have no requirements on these self-adjoint operators to generate any representation of any Lie group. The only thing we need is for this semigroup to make sense. And this is what I'm going to get to right now. So apologies for the confusion, but the nilpotency will be important for the problem of my talk. But this, I wanted to advertise a bit this paper that we released so that I can motivate why I'm interested in this Gaussian semigroup operator. So, so definition. We say a contraction C0 semigroup G from 0 infinity to B of H is Gaussian with respect to the tuple A1 to AN centered around the vector A in Rn if the infinitesimal generator is given by the closure of this operator. So in order to have this be a well-defined C0 semigroup, I will assume that for any vector A, this operator is always essentially self-adjoint on a common domain. So that when I close, I get a unique self-adjoint extension, and this defines a perfectly fine C0 semigroup by Helios-Sida.
But here, semigroup refers to a semigroup of operators, not of channels, right?
Yes, this is a semigroup of operators, yes. So,
But you want it also to be a contraction semigroup, right? So it's
yes.
some accretiveness required.
Sorry, minus. This is a negative self. It's set up so that the generator is a negative self-adjoint operator. Thank you. So as a disclaimer, I will assume that for any A, this expression is essentially self-adjoint on a common dense domain. OK. So now I'm finally ready to tell you what my problem is. Much like the X and P case, there it was straightforward to see that this is nothing but the convolution of the Wigner with a shifted Gaussian, because the shifted Gaussian is a Weyl symbol of this operator. So now I would like to ask the same question for a more general class of operators. What is the natural smearing that I have to apply to my Wigner distribution that gives me this H function? For X and P, this natural smearing was the shifted Gaussian. And this is why you convolve the Wigner with a bivariate Gaussian. So my question now is, what is the natural smearing of W rho so that I can get H T rho? And the answer is straightforward, right? If I know that GTA is the Weyl symbol, if I can find the Weyl symbol of the Gaussian semigroup, of G T A, which is e to the minus t minus a squared. If I know that G is a Weyl symbol for G, then the answer is straightforward, because this quantum-looking expectation, I can write it as the integral of the Wigner distribution of rho against the Weyl symbol of this operator and normalize it by this number. For x and p, it happens that this normalization of the Weyl symbol is a shifted Gaussian. So this is my problem. When does the Gaussian semigroup have a Weyl symbol? So problem, does the Gaussian semigroup G T A, which is e to the minus t ai minus a squared, have a Weyl symbol? With respect to A1, AN. Now, of course, as pointed out, as long as this is a well-defined operator that uses these AIs, I can perfectly ask this question. I don't need any group structure. But my idea to tackle this problem is to assume that these operators generate the representation of a Lie group so that I can use this Q product on my space of symbols that I defined at the beginning of the talk. So my idea to try to answer this question is to consider the case where IA, which is my skew adjoint tuple, generates a strongly continuous unitary representation or simply connected nilpotent Lie group. Unitary representation phi of a simply connected nilpotent Lie group, and translate this problem to a PDE problem. So I will just state a claim. So proposition. If this is true, so if, and I will use star again for this condition, is true, then my Gaussian semigroup will be, and I will call the symbol H or G, will be the Weyl quantization of a Schwarz function G if G solves the following IVP. Maybe I can use here x or equals, and then G TA star x minus a squared. So this is GT of x, GT of x. And this is the skew product. And the initial condition, GTA of 0 is equal to 1. So I hope to convince you that this problem of asking about the existence of a Weyl symbol for this Gaussian semigroup, in the case when my self-adjoint operators generate the symmetries of a nilpotent Lie group, in other words, give me access to this Q product, is equivalent to this IVP. If this IVP has a solution G, with some regularity condition, of course, then that G will be the Weyl symbol of this Gaussian semigroup. And this star here is the skew product that I introduced at the beginning of the talk that intimately uses the structure of the exponential map between the Lie algebra and the Lie group. And if you recall, this Q product, we had an explicit expression for it. And so I would just like to recopy this problem, but apply the Fourier transform to it. And it will turn out that we will get a familiar-looking class of PDEs, PDE. So taking Fourier transform, then we obtain the following. Partial t of g hat of txc, or we can put txc, is the following, minus a squared h hat txc. This is just a fixed number. Minus 2ia gradient with respect to eta h hat t of p c eta, evaluated at eta equals to 0, plus Laplacian in eta of t p at eta equals to 0. And the initial condition is a Dirac delta, and this is C in Rn. So it turns out that if you take the Fourier transform of this problem, by using this explicit expression that I introduced for this Q product, I can rewrite it in terms of a linear second-order PDE with polynomial coefficients on Rn. And what's happening in these expressions here, a is just a number, so I have just a copy of my function, and then one gradient in eta, where eta is the second vector in this polynomial fed to the argument of h, evaluated at eta equals to 0. And then the third term is Laplacian in eta, again in the second component, evaluated at eta equals to 0. And so if you carry out the chain rule with this gradient and Laplacian and bring out derivatives of both p, you will end up in standard form with a second order parabolic PDE, linear parabolic PDE, with polynomial coefficients on Rn. So because of this, I will ask one last question, and this time I will not have any answer. Can we say anything about existence and solutions and uniqueness, sorry, of the IVP? And with that, I conclude my talk, and hopefully there will be some time for questions. Yes.